Hello, Stats. This is 3-2D Notes, Regression with Technology, or another name for it would be wrapping up regression, because that's what we're doing today. We're wrapping things up. So in the warm-up, you saw some Desmos stuff, and I'll write it here just so that you can remember. Desmos, you can make a table with X and Y, and usually it defaults to X1 and Y1, and you put your data in there. It's really convenient to copy and paste data into Desmos. You should try it sometime. It's like so fast. It's amazing. And then the way that you make a regression line is by doing Y1 and use, instead of the equals, use this tilde thing that's in the top left hand of your keyboard. And then you can do mx plus b, or you can do what our book does, which is a plus bx. And don't forget to put a 1 on it. And that will automatically make the regression line. And I made sure that that's in the warm-up, but I wanted you to have it written somewhere also. Calculator can do regression lines. And so you would put your data in list 1 and list 2. That's in Stat Edit. In case you forgot, you're going to get so good at Stat Edit this year. It's going to be amazing. And I actually already have some data in there that I can show you. I put the used car data from the other day into the calculator, and they're not perfect, so I'm not going to get quite exactly this same equation, because what I did is I estimated from the graph, and I estimated like this is 15,000, but it's really probably 14,9 something, and I don't really know exactly. I don't care, but it'll be close to that data that we've seen before. And I want to remind you of some stuff that you maybe already knew. You can get the scatter plot by doing second y equals and choose a plot. Of course, lots of choices here. The first one is the scatter plot, of course, and list 1 and list 2 asks you what you want. And then remember that the zoom 9 is the one that you want. So basically you go to second y equals, you set up your plot to say that you want list 1 and list 2, or whatever lists you're using. And then you do zoom 9 to set up the window automatically. I may have talked about that before, but I'm putting in these notes just to make sure. I know we talked about it with histograms and things like that. Zoom 9 is the stat zoom that automatically sets up your stat window. And that's the graph that we saw before with our, when we had it on Desmos or wherever it was that we had this data before. That's the graph. Okay, so that's the scatter plot, and that's not what we wanted to know. We wanted to know how to find the least squares regression line. Least squares regression line. So what you do is you go to Stat Calc and Stat Calc. 4 is okay, ax plus b, except our book uses a plus bx, and so I like number 8 better because of that. Notice lin is linear and ln is not linear. It's logarithmic. You do not want the logarithmic one. You want linreg, so you're going to choose number 8, which is linreg, linear regression. A plus bx is the one that we prefer in this class. And when you choose that, it asks you again which lists you want. That's great. Optional, you can tell it to store the regression equation in a certain spot, and that's, I guess I'll show you, but it's not something you need to be able to do. It's in vars and then y bars, and you can go over here and get y1, and basically that's saying put it on the y equals screen so that it'll graph, that automatically graphs it for you, which is kind of nice. Calculate. And if you have diagnostics turned on, like I told you to turn them on when we did R, it also calculates R for you. So my R value is negative 0.87. My R squared is 0.76. We've seen those numbers before. It happens to give you, I'm using the used cars data, and it happens to give you what A and B are, and the equation in case you forgot which one you chose. So if you forgot whether A was the slope or the y-intercept, you can look at that. It doesn't put the hat on the y, which bothers me. But the A is 18.765 and B is negative 0.086, and then you have your X. And remember, in context, this was the price or the predicted price if you want to be specific. And this was the mileage in thousands. Actually, this is also in thousands. Which means that I almost have the same equation that's on this. 18,770 got changed to 18.7, and see, it's a little off because I changed the units to thousands, and also because I estimated off the graph, but that's not important as much. It also gives you, when you do this stat calc thing, it also gives you R and R squared if your diagnostics are on. So R happened to equal negative 0.87, and R squared happened to equal 0.76. And remember, we talked about R tells you the strength and the direction. That negative is important for the direction. R squared is the percent of the variation that can be explained by the line. And so that's 76% of the variation explained by the variation in price explained by the miles. So I wanted to review that too. And then one more thing with the calculator. The calculator can do a scatter plot. It can do the least squares line. It also gives you this, and it also can give you a residual plot. And that's something that we've talked about interpreting them, but we haven't talked about graphing them very much. So the residuals have already been saved by the calculator, and it kind of feels like magic. But if you go back to second y equals and tell it again to plot, and instead of the y list, what we want is the y-axis to be residuals. You can get to those residuals by doing second stat. And if you go down, one of the things on this list is the residuals from the last linreg that you just did. I don't know what the stuff under that was, but anyway, resid comes right there. So let's write that down. We want to do a scatter plot of list one and resid, and it stores those every time you do that stat calc linreg command. It stores the residuals. You can get to the residuals by doing second stat. And so what I just did is I did second stat. I'm gonna actually do that whole thing again just to make sure. So we've got this. We choose plot one. We choose scatter plot. We choose our x values and our residuals. And then once again, Zoom 9 will set up the window automatically. So there's the residual plot that went with that plot we just did a little while ago. So that's the residual plot and how to do it on the calculator. Desmos makes it pretty easy to plot residuals also, but I'm not going to show you that right now. And then, so that's Desmos and the calculator. There are a lot of other computer software things out there that are used by people who do stats in real life. And I'm going to show you how to find what you need on a typical computer output. I'm not going to show you how to put it into the computer because we don't have that software available to us. You have to like buy it, and it's kind of a pain. But what happens a lot in the book and also on the AP test is they give you output that came from one of these programs. So let me show you what that looks like. Usually there's a column called predictors. Sometimes this has a different label on it. Coefficients. There's some other stuff over here that we're going to learn later and not yet. I'm just going to write it because it's going to be there. And what always happens right under predictors is you have the word constant. And if you remember from Algebra 1, looking at an equation like this, or maybe Algebra 2 or somewhere later, I don't know, the constant is the one that doesn't have the x on it, which is the y-intercept. So the y-intercept will always be right here next to the word constant. In this case, it would be 18.765. And then underneath that, you'll have another word that represents what x actually is. And so this might say mileage or something like that. This tells you what your x, the name of your x variable. And right next to that name is the coefficient that goes with x, which is the number in front of the x, or otherwise known as slope. Negative 0.086 would go here. And there's usually a lot of other stuff on here. There's some numbers over here that we're not going to worry about yet, and I'm not even going to figure out what those will be, because we will learn this later, I promise. Right now, you are going to focus on this column right here, because always there is a column of coefficients that basically tells you the y-intercept and the slope. This is A, which is the y-intercept, and this is B, which is the slope. And when you're looking at computer output, that is all you need to know about it right now. Later on, we will learn what these other things are for, but not yet. Right now, you're going to be able to look at this and write an equation. So from that, you would get your equation that looks like 18.765 minus 0.086x. Look, that's the same equation I wrote up above because I used the same example again. But I wanted you to see that that's what it looks like on computer output. It always has the y-intercept and the slope underneath the word coefficient. And for this chapter, you can ignore the rest. Later, in a later chapter, we will learn what that other stuff is for. All right, so that's all the technology stuff that you need to know. And then I have one more thing to talk about, and we'll keep these notes kind of short compared to some of the ones I've done lately. I promised you the other day that I would talk eventually about why it is called regression. And it's kind of an interesting story, so I'm going to tell you a story. It has to do with somebody who was studying son's heights versus father's heights. And I'm going to draw a graph, and it's not going to be perfect, but make it kind of big so we can write all over it. There's not a huge correlation between these two variables. It kind of makes this wide oval ellipse sort of thing that looks like this. Not a very strong correlation, but there is a slight positive trend. And this scientist, I forget his name, sorry, was studying father's heights and using them to predict son's heights. And as you might guess, the positive trend comes from the fact that shorter people tend to have shorter children, and taller people tend to have taller children. And that's predictable, right? In fact, you could even say it would be what you might expect that would happen is the y equals x line, which is what would happen if every father's height was exactly the same as his son's height. So like this person right here, the father is this tall and the son is the same exact height, and same with this person right here, and so forth. You might expect that that would be the best line. In fact, that line is also, if you draw an oval around this thing or an ellipse, that is also the axis of the ellipse, which means my ellipse is not perfect. I should have a few more dots down here. But anyway, you'd expect it to follow the direction of the ellipse. But what's interesting is this scientist who was studying this said it doesn't really work that way. It's kind of interesting. You would expect this to be a good line of fit, but if you look at this group of data right here, is this a good prediction of this distribution that's right here? No, we're over predicting the height of sons who have really tall fathers. And that's interesting. Maybe I should move my line a little lower so I predict this group better. Maybe I should have it more like there. Same thing happens at this end. If I look at this group of people over here that have really short fathers, is this a good prediction of the son's heights if they're ranging from about here to about there? No. You're more likely, if you have a super short father, you're more likely to have a son taller than him. And if you have a super tall father, you're more likely to have a son shorter than him. So the actual line of fit, it still goes through the line of means, which we've talked about before, right? The line of means would be right here. But it doesn't go as steep as you might expect. It goes slightly less steep so that each, if you think of these in strips, here's a calculus concept for you. If you think of these in strips, each strip, it should go through the middle of that strip so that it ends up going more like this. This is the best prediction line, which is the least squares line that we learned about. And it's not as steep as you would get if you were using the y equals x line. So that's interesting. So it is steeper than if you just use the mean. I mean, if you didn't know the father's height, then your best guess for that son's height would be the mean. This is the y bar line. And that's not a great predictor either. You want to be in between the y equals x line and the y bar line. And that in between is called regression towards the mean. In other words, the son's height is likely to be closer to the mean than the father's height. And that is really interesting. So it was called a regression line because of regression towards the mean. Now, this doesn't happen only with fathers and sons. It's not always a cause and effect thing. I've seen this same type of graph happen with a sister's height and her other sister's height. And then maybe you have to think about I wonder why this one was here and that one was there. You could switch the sons and the fathers and you get this same result. Have you ever noticed that if you get really high grades at the beginning of the semester, it's hard to keep that up? and your grades tend to fall down towards the mean as the semester goes on. And if you start out with a really low grade, your grade is likely to go up later on. And so that happens with that. It happens with grades. It happens with heights. It happens with all kinds of things. All kinds of things that don't have a super strong correlation end up going closer to the mean later on, because the best prediction of this group of people is in that area. So it's based on that. And I just find it really fascinating that that happens. And that is the reason why the correlation is part of that slope formula. The correlation says we're not going to go this steep unless we have a really super strong correlation. If we have a weaker correlation like this one, we're going to go closer to the mean to make up for that extra spread in the dots. So that was kind of a little sidetrack and interesting, not something you have to know, but I think it's interesting, and so that's why it's in these notes. And then the next lesson will be the review lesson, and the warm-up and notes are kind of the same thing. They all count as the same thing. So we'll do warm-up that counts as notes in the next lesson coming up.